Excellent. I live on Oak Street in Geneseo, and it is ground zero for Halloween in Livingston County, quite literally. And on a good year, we'll get like 300 trick-or-treaters up and down. It's a fantastic night. It wasn't quite that much busy last night, but we had more than half of what we would normally get on a regular night, so that was good. We devised a candy chute, so we stood on the porch and basically fired candy down a long PVC pipe towards the kids. They seemed to actually really enjoy that, so that was nice. I mean, we might keep the candy chute around next year just because it was so much fun. So nice to have a little bit of normalcy in what has been a very weird semester, and very weird 6 to 8 months. Yeah, tomorrow's election day. Hopefully you have already cast a ballot. If not, you've made plans on how you're going to do that. Very important to participate in this democracy of ours and make it work the best it possibly can, no matter what the outcome. Though we'll be back here Wednesday learning physics, so take it all in stride. There's a new Kappa up. It'll be due this Thursday as usual. Any questions or comments or? Okay, let's get to it. So we left off on Friday talking about radiative emission and absorption, and we wrote down a single equation. That was this one. P equals sigma epsilon A T to the fourth. Sigma, so this is, and we wrote this same equation down in two different contexts. One, in the context of how much radiation is emitted by an object, how much energy per second is emitted by an object due to its own thermal energy. And the other in the context of how much it absorbs from the environment due to the environment's thermal energy. They're exactly the same formula. Epsilon is exactly the same. It is the emissivity of an object and is related to its composition, but more importantly to the surface texture of the object itself. And it is a reflectivity at some level, or an absorptivity at some level. It's an anti-reflectivity. A number between 0 and 1, with 1 being a perfectly absorptive thing. And we saw some cool videos about an object that actually did have a 99.97% absorption rate and what that actually means and what that looks like. Sigma is just a constant. A is the surface area of the object, and T, of course, is its temperature. The temperature of the object, if you're talking about how much energy it's emitting. The temperature of the environment, if you're talking about how much radiation, how much energy per second it is it's absorbing. So let's do an example. A toaster, specifically maybe a toaster oven. Doesn't really matter though. So we'll do the simple case first. What if we have a toaster at room temperature? A toaster not on at room temperature. Let's say it's 20 degrees Celsius. What will be the equilibrium temperature of the toaster? You probably don't even have to do this equation to tell me what the equilibrium temperature of the toaster will be if it's sitting in a room not on in a temperature 20-degree room. It'll be 20 degrees. Well, let's do the problem anyway and see how these usually work. So these are usually equilibrium temperature problems. You've got some incident energy, you've got some radiative energy. There will be a temperature at which those two things are equal to each other, and that will be the equilibrium temperature of the object that you're talking about. So we just have to set these two equations equal to each other. We know that the rate in equilibrium, what does that mean? It means that the radiative power is equal to the power that's being absorbed. Oops. Okay, we're just gonna leave that there. Okay, so we know that the radiative power that's radiated away is epsilon of the toaster times sigma times surface area of the toaster times the temperature of the toaster to the fourth power. We know that the power that's being absorbed is exactly the same thing. Epsilon of the toaster, sigma, surface area of the toaster. But it's the temperature of the room in this case to the fourth power. We know those two things are equal to each other. We can just set them equal to each other. Epsilon toaster, sigma A toaster, T toaster to the fourth, epsilon toaster, sigma A toaster, T room to the fourth, divide through by epsilon, divide through by sigma, divide through by A. They're all exactly the same in this case. And we get temperature of the toaster to the fourth power is equal to the room to the fourth power. Take the cube root of both sides, and you get the not surprising result. The temperature of the toaster is equal to temperature of the room. Great. That's not that interesting. Let's turn the toaster on, though. What's going to happen? So what do I mean by turn the toaster on? I mean, I'm going to heat it. I'm going to add energy to the inside of that toaster to the tune of 200 watts. Right? So every second, I'm going to add 200 watts, joules of energy to the toaster. What will happen to the temperature of the toaster? Obviously, it will go up. But if I continually forever add 200 watts of power to the toaster, will this toaster eventually reach a temperature of infinity? No, I see two no's and no yeses. You want to make an argument for no? Right. Well, no. Let's say the temperature, the power is being entirely. It's an oven. It's an insulated oven, and we're adding it to. Well, it's insulated in the sense that the power is going inside the toaster. The toaster will break eventually. It's going to eventually reach a temperature of infinity or something. Something's going to happen. What's going to happen? Go ahead, Alex. You got your hand up first. Yes. As the temperature gets hotter, though, it will radiate more energy. And as it radiates away more energy, there might come a point at which P rad equals P absorbed again, and that might be a new equilibrium temperature for our toaster. It shouldn't actually be the case, even if we for infinite time add energy to our toaster, that our toaster will, in fact, get to infinity temperature, because the toaster will begin to lose some of that energy by radiation. So let's see if we can set this up. So we know that the total power out has to equal the total power in equilibrium, if equilibrium can be established. Our P in is the same as it was before. We know that we're absorbing some epsilon T, sigma A T, T room to the fourth power, but now we also have the power that we're adding from the outlet, and that we plug this thing into, adding temperature, adding power, adding energy to our toaster oven. Our P out is exactly the same as it was before. Epsilon sigma A T to the fourth power. T temperature of the toaster to the fourth power. Aha. Now we should no longer have a temperature of the toaster at equilibrium that is equal to the temperature of the room. But what will that new temperature be? Well, we have everything we need now to figure out what that new temperature is going to be. We just have to solve this for T temperature, T toaster. Some simple algebra, we get to, I don't know if it's simple, but it is algebra. Temperature of the toaster is temperature of the room to the fourth power, plus pH, how much energy we're adding, divided by epsilon T sigma A to the of toaster, all to the 1/4 power. So it should be exactly what it was before, plus some other term that's going to be dictated by how much energy we're actually adding to the toaster itself. Okay. Now, you plug in some numbers. I actually didn't even do it in my notes, so I don't even have a number for you. You can plug in numbers if you wanted to. Just be aware, we could do not plug in 20 degrees for the temperature here. These all require you to use Kelvin. This is a true absolute temperature. This is not a delta T. You can no longer get away with using Celsius. You have to use temperature in Kelvin in order for this to work. You have to plug in a T room in Kelvin, and you're going to get out a T Kelvin. You can convert that to Celsius after the fact, but you have to, this equation demands Kelvins. You cannot use Celsius here. Okay, great. So, that is the end of our examples on radiative absorption. Was only one, well, 1.5. Okay, let's switch gears now and pick up a new topic. Thermodynamics. We've been considering heat flow in and out, but what we're going to add to the situation, we're going to add to the mix now is the ability for our system to do work, the ability for our system to expand and contract. And that's going to fundamentally change the thermodynamics equation, the thermal equations that we've been thinking about. So we've so far been thinking about Qs. Meaning energy, thermal energy simply added or removed from our system or transferred from one part of our system to another part of our system. Now, let's bring in work. What if our system does work? So recall from Analyte 1, you probably wrote down something that was like this. Some d work, some infinitesimal work quantity is equal to some force times some infinitesimal displacement. Does that look vaguely familiar from Analyte 1? Okay, good. This works pretty well if you want to talk about point masses and throwing things up in the air and moving them from one point to the other and forces and distances. Doesn't work so well for a gas, right? If you have a balloon and you heat up the gas in the balloon and it expands, right? What is the ds in that case? Well, we don't really want to think about individual displacements. We want to think about this in terms of continuum dynamics and bulk motion. So for fluids, we can write a similar equation. And that is that dW is equal to, what's the equivalent of force for a fluid? Pressure. And instead of talking about a displacement in space, remember a P is a force per unit area. We can think about this as being instead of a linear displacement, a volumetric displacement. P times some infinitesimal change in volume. The units work out the same. It actually works pretty well. It works exactly. This is right. Notice that, interestingly, work is not a vector quantity. even though you used vector quantities to calculate it in Analyte 1, neither of the quantities that we're using to calculate work here are vector quantities. Pressure and volume are both scalar quantities, and so is work. So we don't have to worry about that. That's nice. So just to remind you, P equals pressure, V equals volume. And to remind you that P equals force divided by area. Okay, so let's set this up. Let's say we've got some sort of device here with some gas inside it, and let's say it's covered by some movable piston, right? So this is some movable thing, right? And we've got some gas in here. Let's say, I don't know what it is, doesn't matter. Some gas. So, so if we slowly let this piston rise, write this all out. If we have a piston and increase the volume, of the gas, work, and this has all got to be done slowly so that you're not shot, you're doing this all sort of in some thermodynamic equilibrium state, even as you go along, then work is done by the gas. Not walk, work is done by the gas. So in this case, dW is positive. Anytime the volume of our substance increases, work is being done by our substance, right? It has to do some work to move that piston up, that lid. Since that's the case, the total thermal energy of the system has to go down. This is different. I warned you about this earlier, and we're now exploring it. Work is the opposite sense as it was in Analyte 1. In Analyte 1, if I did work on this, it was work done on something, right? I do work on this pen, move it up to a higher elevation, it gains energy. In this case, it's exactly the opposite. The work is done by the system, and so any work that's done by the system on its environment has to be energy that's removed from the system itself. Work is done by a system, not on a system. In this case, I'll say this work. Okay, so don't get confused by that. Okay, this leads straight to, we've already seen the 0th law of thermodynamics. This leads straight to the first law of thermodynamics. And that is that dE, thermal energy, I'll use subscript TH, the change in energy is equal to Q minus W. Let's define these terms real quick. E thermal energy is the total. Okay, well, so let's think about this. Work is some energy amount of work that's done by the system. It's taking into account the volumetric change of the substance. And Q is the amount of energy that we're adding to the system by normal thermal processes, either by conduction or radiation or some other process, right? This is basically an energy conservation equation. It's not basically, it is an energy conservation equation. That's all this really is. Energy is conserved. You can change its form from thermal energy to work to Q, but the total energy, which is E, has to stay the same. Okay, so E is the total thermal energy in the system. This is a state variable. You can talk about a glob of a substance sitting here and talk about its ETH. You can talk about other state variables like pressure and temperature. It's a measurable quantity of a substance in a particular state. We'll talk more about state variables in a minute. Q is exactly as we defined it before, the heat added or moved. And work is the work done by the system. Are Q and W state variables. Why not? Exactly right. Q cannot be an innate property of the system. You can't talk about a lump of blob of something you've got on a table and talk about the Q of it. It doesn't even make sense. Q is just a transitional quantity. It's only defined even as you are adding or removing something from it. The same with W. You can't talk about the work of a substance. You can only talk about work in the context of something changing. Work is a change in something. Q is a change in something. E, though, is a fundamental property of the thing. It's important to keep these in mind because it's going to be confusing. You're going to be thinking of Q as an energy, and you're going to be thinking of E as an energy, and sometimes you're going to be thinking of W as an energy, but only one of those is truly the energy of the system. The others are just ways of changing the energy in the system. They're always deltas in that sense. Q and W are not state variables. Okay, so how are we going to go about calculating these Q's and W's? How are we going to know how much energy, heat energy we've added? How are we going to know or calculate how much work we've done or has been done on the system? Let's think about these. How can we measure? And honestly, dq often shows up in these equations. What is the d? Some differential q. That doesn't even really make sense. It's a redundancy. Q is already by definition a differential. You could just as easily write this q minus w. There really isn't a need for the d and the w either, right? A change in thermal energy is related to the q and the w. dq and dw is redundant. It doesn't hurt to have it there, but you don't really need it. Q is already, by its very definition, a change in something. But I'll put it there anyway. This dq, you can infer usually from delta T, right? We've already seen how adding heat to a system, adding energy to a system will change its temperature based on its specific heat. But this is going to get more complicated now. We've been talking about solid objects and changing temperatures and things with solid objects. Now that we're talking about gaseous substances which can compress, it becomes more difficult. Are we talking about the specific heat at constant pressure. We're talking about the specific heat at constant volume. Those two things can be different for gases. In fact, they will be different for gases. And so you can't necessarily infer what Q is just from a change in temperature. It's going to depend on how specifically you're making that transition happen, what the Q actually is. So this is where it's going to get complicated. Sometimes. But in general, we know only CP or CV, meaning and those two and CP is often not equal to CV, and it's possible to change a temperature without holding both one of those variables constant. It's possible to change both the pressure and the volume, and then what do? It's not obvious. It's not clear what happens then. There is no specific number you can just plug in there. What if both change? How about W? Well, we know that dW is basically just PdV, right? So if you know the pressure and you know how the volume's changing, you can probably do some integral to get work from some pressure and change in volume, but the pressure is probably going to be changing, often will be changing as you change the volume. And so you're going to need to know how pressure and volume are related if you really want to be able to do this calculation well. Need to either hold P constant, in which case it's easy, or know how P and V are related. And that's going to depend on the material, phase, etc. So we'll talk more about those kinds of equations later on. How you get there matters, though. Okay, let's talk about some different types of processes. And let's introduce what's going to be our friend for the next week or two. And that is a specific diagram where we're going to be plotting the pressure on the y-axis and the volume on the x-axis. This is known in the business as a PV diagram for obvious reasons. Have you seen these in chemistry? Do you do PV diagrams in chemistry? I hope so. They're extraordinarily useful things. Okay, so let's think about types of processes. Again, we're thinking about the picture to have in your head is this one, right? We've got some gas contained in some cylinder, and we can change the volume by either squeezing it down or letting it expand. We can change the pressure, and we can add or remove thermal energy. We can add Q. We can add Q to the system by putting it in contact with a thermal reservoir, or we can let work be done by letting it expand or push it down. We can move in both directions given this thing. So as we're talking about moving around in the PV diagram, I want you to have this thing in your head and be thinking about how you could make that happen with a system like this. So types of processes. One, you could have a process that doesn't change the volume, so constant volume. There's a name for a process where the volume doesn't change. Anybody know what it is? Isochoric, that's exactly right. Iso meaning the same, choric meaning, I guess, volume. I don't know. I don't speak Latin. It's probably Latin. So what is that going to look like on the PV diagram? Well, it's pretty simple. Any process that doesn't change the volume is going to be on this diagram a vertical line. It's either going to move up or down. That's an isochoric transition, either moving up or down in the PV diagram. We can say some things about this. What is, for instance, dW? We know that work is PdV. What is that for an isochoric process? V isn't changing. So yeah, you're going to integrate from one volume to another, and those two are going to be the same volumes. So what are you going to get? Almost. It's going to be 0, right? And if there is no change in volume, there is no work done by the gas, right? You're integrating, you're doing an integral, but you're integrating from in the exact same thing. And so you're going to get whatever the pressure is, you're going to get that minus the same thing. It's going to go away. Isochoric processes are always 0 work done. What is that? You know, moving up or down in this diagram, again, you're keeping the volume constant. You are holding that steady. No work is being done on or by the gas. You're just adding thermal energy to make the pressure higher or lower, or removing thermal energy to make the pressure higher or lower. Okay. This is all heat, no work. Excellent. Okay, next one. How about the next simplest one is constant pressure. We know what we call these? Go for it. Isobaric. Barometer is a pressure meter. Baro must be some root that means pressure. Iso meaning the same. Constant pressure. Isobar, if you ever watch the weather on the news or on the Weather Channel, they'll show you those constant lines are isobars, lines of constant pressure on the map. So what does that look like on the PV diagram? Again, this is the other simple one. Constant pressure will just be left or right on the PV diagram. So in this case, PdV is not 0, but it's easy to calculate. It's easy to calculate because pressure is a constant. If you've got an integral with P times dV, you can pull the pressure out if it's not changing. If it's constant, the integral of dV is just the volume. And so, or the change in the volume is basically P delta V. But easy to calculate. It's basically P delta V. dQ is probably also not 0. But we'll talk more about that in a minute. It's not obvious from here that that has to be the case, but it usually is. Okay, how about adiabatic? This is another common one you run into. Adiabatic literally means all work, no heat. So in this case, Q tote equals 0. And the only way you're changing the energy of the system is by letting it do work or doing work on it. You might think this would be a perfectly horizontal line on the PV diagram, but it's actually not. We'll talk about what it is later. Okay, some other things that we'll run into. Isothermal. This one you can probably guess. Iso meaning constant, thermal meaning temperature. This is a constant temperature transition. It often implies, usually, that dE is 0. Turns out if you let an object do work and add heat or remove heat at just the right way to keep the temperature the constant, that usually the total energy of the system has not changed either. The other thing we're going to talk about is cyclic. We'll talk about some cycles, things like engines and refrigerators. So basically, you go through a path on a PV diagram and return to where you started from. That's a cyclic process. Return to original position, location in PV diagram. What does this imply about delta E for the trip? If you start out in a particular location and you go through, doesn't even matter what it is, some loop and come around back to where you started from, E is a state variable. And therefore, if you return to the same pressure volume state, you have to also have returned to the same energy state, E state, because it's a state variable. You will not necessarily have done the same amount of work or the same amount of heat added in this process, but you have to have returned to the same energy state if you return back to the same location on the PV diagram, which means the total net change in thermal energy for the entire cycle must be 0. So, which implies, since we know that dE is Q minus W, in this case, Q must equals W, as it is in the isothermal. Anytime dE is 0, whatever heat you're adding must be offset by whatever work you're doing to the system, having to be done by the system. Okay, let's do some examples and think about how this works. Okay, so here is a PV diagram. And let's think about going in a loop. There's 1, there's 2, and there's 3. Let's number these 1, 2, and 3. So some substance undergoes these 3 changes. It changes in, let me make sure I label these axes so I remember what we're talking about. It changes in volume without having changed the pressure at all. Then it changes in pressure without changing the volume at all, increasing both times. And then both of those are decreased to get us back to our original location. So let's think about each one of these in turn and assume that it's a normal substance. So this is no weird thing where, when you heat it up, it gets smaller, or when, you heat it up, it loses temperature. This is a normal substance where alpha and C are both positive. What's going to happen? In fact, what I want to know is, at each stage, 1, 2, and 3, these 3 variables that we're interested in, Q, W, and delta E, I don't need numbers yet, but I would like to know, are they positive, negative, or 0 in each of these cases? So let's do the easy one first. Let's do number 2. We are taking a substance, we are increasing the pressure without changing the volume. What can you say about the work? Work has to be 0. Anytime you are not changing your volume, the work being done by your gas is 0. So we can fill in the middle thing right away. We know that this must be 0. Now, is the total energy of the system, do you think, higher or lower as the pressure is getting increased? Why would you say higher? You're right. Yeah. What do we mean by energy? We mean some sort of thermal kinetic energy of the molecules inside. As the pressure goes up, that must imply that those molecules are moving around, those atoms are moving around faster. It must be that there's some higher energy associated with them. That's exactly right. So we think, we know, delta E must be positive as we move up in the diagram. What does that imply about Q? It's got to be positive. Remember, at this point, we should always be thinking back to the first law of thermodynamics. E equals Q minus W. If E goes up and W doesn't change, Q has to go up. Okay, let's think about step 1 now, right? We are increasing the volume at constant pressure. What can we say about the work now? It's not 0 anymore. Do we know if it's positive or negative? Right. So the argument is the change in volume is positive. P equals, work equals PdV. Since the change in volume is constant, is positive, pressure has to be positive. That must be that the work is positive also. That's right. If you move to the right on this diagram, if you increase the volume, your substance is doing work to increase its volume. And that's positive number. If the substance the volume gets smaller, if you move to the left of this diagram, it must be that that there is negative work done. You are doing work on the system. There's negative work being done by the system to make it smaller. So that's right. W has to be positive for 1. What about Q and DE? This is a little bit tricky. Let's try to think about this though. What if we had increased the temperature at constant volume? Sorry, what if we increase the volume at constant temperature? What would happen? If we let our gas expand and don't add any thermal energy to our system, let's say Q were 0, what would we expect to happen for the temperature of our object? Yeah, that's exactly right. So let's think about this carefully. As we let our volume expand, let's say we're not adding any thermal energy to it, what's going to happen? Thermal energy has to be being removed from our system. Remember, E equals D equals Q minus W. If Q is 0 and W is positive, our total energy is going down, right? What does that imply about the temperature? It must be that the temperature is also going down, right? And so it must be, therefore, that if we were to increase the pressure without adding any Q, we would end up in a state that's actually less energetic. It must be down here somewhere if we didn't add Q to the system. In order to keep the pressure up as we increase the volume, we have to add some thermal energy to the system. It just has to be the case that Q is positive if we're going straight across the line. If we don't, thermal energy will be lost. The pressure will have to go down as we increase the volume. And so Q has to be positive. What about DE? It's not necessarily the case. I mean, this is where different substances can behave kind of differently. We can't use the first law of thermodynamics, right? DE is Q minus W. They're both positive. We can't just use the signs to get an easy answer here. But it turns out for these arguments, again, if you have delta E equals 0, you usually end up somewhere down below. The delta E has to go up a little bit if you've stayed at the same pressure that whole time. So this isn't necessarily a given, but almost always you'll see that that's delta E is positive also. This has a higher energy than it did when it started from on the other side. Okay, but at the very least, it's not going to be much because whatever Q you're adding, you're taking that away with the work. Okay, so we can do number 3 now. What's true of the work as we go from this point to this point? It's got to be negative. Anytime we move left at all on this diagram, work has to be negative. Anytime we move right at all on this diagram, work has to be positive. Since we're moving generally left, that has to be a negative work. What about delta E? How can we tell what delta E is? Between for leg 3 from there to there. Exactly right. We know that this is a cyclic process to go through this whole thing. We know that the DE total of the whole system has to be 0 if we've come back to the same place on the PV diagram. Since it was positive in both of the other legs, it has to be negative going back towards where we started from. And this is where the first law becomes really simple. If total energy has gone down and work is negative, that means Q must be even more negative because a negative work will actually add energy to the system. So we have to be removing huge amounts of energy thermally from this thing as we go on stage 3. Okay, so this is going to be an important diagram. It's important to be able to look at this diagram and sort of understand how your system is going to be changing in energy and work in Q as you move to various points in the diagram. If it doesn't make sense yet, run the scenarios over and over again in your head and try to get it down. This table hopefully will help, so you're looking for left, right. W is really easy. If you're moving left, it's negative. If you're moving right, it's positive. If you're moving up and down, it's 0. The other two can kind of be inferred sometimes from the first law of thermodynamics and other times from understanding how isotherms and things work. But we'll talk about that in a bit. Okay. How much time do I have left? I have almost no time. So I've said this before. There's some concept questions we'll ask to start a class on Wednesday. I've mentioned this, but I want to write it down in particular. We know that dW equals PdV. PdV. It is the case, therefore, that W is the integral of P times dV, right? If you integrate both sides, you get integral PdV. Well, interestingly, what have we got here? We've got a PV diagram. What is the integral of PdV in graphical terms on this chart? For any of them, it's the area. It's just the area underneath that curve. So we can calculate it as a specific thing for each specific one of those. But even if you had some curly Q thing where you're doing this, it doesn't matter. The work is going to be the area underneath the starting point, the curve that you attach between the starting point and the end point. And how you get there is going to change the work you need to do to get there, and is therefore going to change the Q that you need to get from where you've started to from where you're going. Because the total energy at the beginning and the end point have to be the same, but the Q and the W don't. The Q and the W will be determined by the path you take to get there, because Q and W aren't state variables. Okay, we'll explore this principle more on Wednesday.